And as a second topic of today, let's discuss about eccentric loading. Eccentric loading means it's not centric loading. And what's the definition? The definition is simple. When line of action does not pass through the centroid, we call that as eccentric loading. Suppose that we have this interesting wavy structure, and we have a pair of forces P in the left and right side, and when we have these two forces, we have a line of action like this dotted line, and if we make an imaginary cut here, what you can realize is loading does not pass through centroid of this guy. Okay, then what's going on, what's happening there? You can see here is that like the normal force N must have the same magnitude with the P so that you can have the force equilibrium. However, you cannot satisfy mechanical equilibrium when you only have the normal force N. This is force acting on the centroid, because when the pair of this N and P try to rotate this part in clockwise. So to balance this out, you need a torque, local torque in counterclockwise, and you have to initiate this local torque by stress distribution around the centroid. Okay, so y equals 0 here is the centroid location, and if we draw the stress distribution, it looks like this. So from the normal force N, you're gonna have uniform force regardless of the position y. From the moment M, you're gonna have a stress linear in location y, and if you combine these two based on the superposition principle, the sigma x can be written as minus y over I multiplied by m. This is Flexure formula, and this is p over a is the uniform stress, and this is what you're gonna get. Sigma x equals to be minus y over I multiplied by m plus p over a. Now for these kind of eccentric loading problem where both n and m are non-zero due to eccentric loading, non-zero n is not enough to make a mechanical equilibrium. Okay, so you can now see how we can analyze the problem and how to obtain stress distribution. Of course, this is not enough as an example, so let me give you a problem with real numbers. So this problem asks us a stress distribution for this kind of a structure, and this problem asks stress distribution in this imaginary surface. And here line of action, of course not going through the centroid position, and the distance from the centroid to line of action is 16 millimeter. And the cross section is given as a perfect circle with radius 6 millimeter. And for this perfect circle cross section, the area moment is given as pi over 4 multiplied by radius 4th power. Okay, so how can we approach the problem? We can use the free body diagram that we drove in previous page. So when we have a force P here, then to achieve the force balance with 700 Newton, we need 700 Newton normal force. And you can see this normal force and that applied force P, they somehow induce clockwise rotation, clockwise torque. So to balance this out, you need 700 Newton multiplied by 60 millimeter moment in opposite direction, which turns out to be 11.2 Newton meter. Okay, so out of N and M, we can obtain stress. So stress from the normal force N, you can obtain A is pi c to the square, and A is 103.1 square millimeter, and the normal stress from the normal force is given as here. And you can also obtain the stress from the moment M, and to use Flexure formula, you need the number for area moment inertia I, and if you plug in C equals to be 6 millimeter, then you're gonna have this number as I, and if you plug this into the stress expression from the moment, this is what you're gonna get. Okay, so this is a stress distribution due to n. This is a stress distribution due to m. If you sum this up, this is the stress distribution you can expect for 12 millimeter diameter cross section. Okay, and you can see that y equals 0 position is the centroid position, and stress is 0 position is, and or stress 0 means the strain 0. This is neutral plane. Okay, so you can see that for the problem with both n and m are non-zero, then you see centroid does not go through neutral plane anymore. Okay, and you can also of course obtain the maximum compressive stress and maximum normal stress by adding up or subtracting these two numbers. And the location of this neutral point, you can find the neutral plane location y0 by solving this equation. This indicates when stress equals to v0, that is the location of neutral point y0. Okay, so with that, let me finish my short discussion on eccentric loading.